So I have time to talk only about actually four of these goals. I'm going to be talking about how we can fight hunger, how we can provide clean energy to the planet, how to fight against climate change, and a little bit about one of the goals, which is usually not very prominent, is how to create partnerships, how we can work together towards achieving these goals. First, hunger. Here we can feel very proud because the chemistry community has a big role in the Green Revolution. A reaction that seems very simple on paper, which is just reacting nitrogen with hydrogen, has been the key for providing food to so many people. This reaction is in fact extremely difficult, as you know, from a thermodynamic point of view. The triple bond in the nitrogen molecule is very stable. The activation energy for this reaction to happen is extremely high. Through the use of catalyst, I'm going to be talking about catalyst during my presentation, we can make this reaction happen and provide nitrogen that afterwards can be transformed into fertilizers. This seems, again, a very simple reaction, but it's been very meaningful. This is one of the plots that should be in every chemistry book. We should be feeling very proud about this plot. If you have not seen it, let me go with you through this plot because it's extremely important. It was published in Nature Geosciences a few years ago. Since the discovery of the Haber-Bosch process, the population of the world has exploded from less than 2 billion people to more than 7 billion people. Some estimations suggest that without the Haber-Bosch process, now we will have only a population of 3.5 billion people. So in a way, artificial fertilizers are providing food for half of the planet. If somebody asks you which are one of the main contributions of chemistry to society, I think the Haber-Bosch process is a very meaningful contribution because it's providing food to half of the planet. Actually, a significant part of the nitrogen in our bodies is coming from a chemical plant. A plant like this one here, a huge plant. And that's one of our challenges. The Haber-Bosch process takes between 1% and 2% of all the world's energy production. The first thing you need to do to produce ammonia is to actually generate hydrogen. There is no free hydrogen in nature. You need to produce it. And it's usually produced through reforming of methane. Well, this is a very pollutant process that involves the generation of large amounts of CO2. But even if we will have enough hydrogen to produce ammonia, this part over here, which is the reactor that actually produces the ammonia, carry out that reaction, operates at extremely high conditions, not so much in terms of temperature, but at very elevated pressures. And as we know, nature does the same thing under much milder conditions. And nature doesn't need hydrogen. It just needs protons. So when we look at this enzyme, nitrogenase, we realize that the catalysis is happening in this cofactor when you have this iron cluster cofactor where the magic happens. There are several iron atoms, and the D-nitrogen molecule can bind to one or several of these iron bonds, and through a very mild, you see activation energies are quite low process, you can carry out this reaction again under very mild conditions. In the last 30 years or so, inorganic chemists has worked very hard to mimic this process, and one of the main breakthroughs in the field, actually now quite old, is this Часть cycle, when with the use of molybdenum and tungsten complexes with this phosphine, you can fixate actually 2 molecules of ammonia per molecule of D-nitrogen, again, without the use of hydrogen. More recently, this has been a main breakthrough just a few years ago, this mononuclear iron complex is able to do the same at higher efficiency, imitating the cluster, as I said before, involves iron. There is something magic about iron and the Haber-Bosch process. Both the heterogeneous and the homogeneous catalysts contain high amounts of iron. But probably the most striking piece of research in fixation of nitrogen is probably this paper, which is actually quite amazing. By reacting nitrogen with water, nitrogen with just plain water, under very mild conditions, for example, at 25 degrees C, using only 1.2 volts, you can obtain ammonia at a 35% yield. That's an amazing yield, much higher than either plants or the Haber process. And it's very beautiful because actually you don't need to use pure hydrogen. You can use just air. Air plus water, with a little bit of electricity, actually a pretty low voltage, you can get ammonia 35% yield. This piece of research is indeed very inspiring.